Everybody, give it up for Paul.
Thanks, everyone. Yeah, so I was originally going to be talking about structuring applications, which is probably what you saw on the website if you're looking. But since I originally submitted my proposal, I've been working on something for the last month or so, just like nonstop. Something called Cadre, which I'm going to talk about today. But I'm also going to be talking more in general about distributed state and Elixir systems and how it gets there, common problems that tend to surface when it creeps into your system if you're not paying very close attention to that. And particularly in that transition between, you're on a single node and then you're scaling up and actually clustering nodes. So to get started, I guess I really want to show you guys this quote I was reading the other day in a paper called Lineage-Driven Fault Injection. And it says, one of the difficult truths of large-scale services is that if something can go wrong, eventually it will. And I think there's a corollary to that, which is that it doesn't have to be a large-scale service for that to be true. It's just the larger the scale, the faster it's likely to happen. So even on small single-node applications, very rare failures can occur. I mean, you might just get really unlucky and the hard drive in your host is toast and your machine goes down, data corruption or something like that. So these are things that can happen to any machine, any application of any scale. And I think this is an important thing to keep in mind. So typically when you're transitioning into a system where you have distributed state, it's because you need to replicate some data across servers, right? Either for reliability, you need some redundancy to make sure that if one node goes down, requests can still be served by another node. Or perhaps because of performance, you want to make sure that data is able to be split across nodes so that you have more computational power to throw at it, more requests can be served because more nodes are involved, or perhaps some combination of both. And one of the key principles here is that almost always when you have distributed state, the expectation is that multiple processes are likely going to be talking to that state simultaneously. So usually the flow is something kind of like this. Depends on the system. This isn't like universally true, but this is generally the true. You have a single node application that you now need to scale up into a multi-node application. We're going to assume that this is a clustered application. If you're not clustering and you're just doing simple load balancing, this doesn't really apply because logically speaking, that's still a single node system. You don't have any communication between the two. So we're talking about clusters here. So you built this single node system and you're using some handy things that are in OTP, ETS, the registry module, probably a variety of other things. And in a multi-node environment, this maybe no longer works, depending on what you're using those things for. Particularly registry, for example, that's specific to a single node. When you go multi-node, registry is only going to work for processes on the same node. If you're trying to find processes that are on another node, say you're splitting processes across all the nodes in the cluster, and you need to be able to find a specific one to send a request to, you need something that's global for a process registry, not local. Likewise, with ETS, you can only talk to an ETS table on the same host. Otherwise, you have to redirect a request either over the RPC channel or to another process that can proxy the request to the table. These are both things that are very commonly used in a single node and multi-node application, but won't necessarily immediately be useful when you scale up to a multi-node. And they're used for a variety of things, service discovery, process registration, caches. Maybe you're storing state in an ETS table just for performance. And here's a variety of other things that you might have on a single node application, but also need now a distributed version of. So global process registry, a cache, locks to acquire and release in order to basically have exclusive access to some important resource, presence in the case of like Phoenix, event logs. If you're working with an event-driven system, your event log is going to be distributed effectively now. And there's other use cases as well. And there's a few out-of-the-box solutions for some of these things. Global, in particular, is seeing a lot of improvements in some of the more recent OTP releases. For one thing, it used to be that when you were registering a process name with global, it had to be an atom, which has problems, namely that you can blow the atom table if you have too many processes. The other thing is that it's not necessarily a convenient way to name processes, especially in a system where you're spawning processes that maybe are identified by like a device ID or a user ID or something. You don't want to be creating atoms based on those things because they're never garbage collected. And additionally, it's not very convenient to convert to an atom in those cases. It's nice to be able to just use a binary or a tuple or something like that. Excuse me. A little parched. So global now actually supports using arbitrary terms for this, which is really nice. It's one of the benefits of the registry module in Elixir. It also has a feature that I'm not sure a whole lot of people know about, but it can also be used as a global lock server. So the way this works is when you spin up a cluster, all the nodes that are connected together talk to each other and share these global names. For distributed cache, Amnesia is maybe a little overkill for this, but it's the only thing that's like out of the box available to you for this. Amnesia, if you're not familiar, distributed database, key value. It's basically like distributed ETS with transactions. And, you know, leader election, or well, more like you select leaders, masters, they call them in Amnesia. I've never used this as a cache, but if I was somebody new to Elixir or Erlang even, the first thing I would see is like, hey, this is basically Erlang term storage, but I can use it in a cluster, and it gives me some nice guarantees that ETS also provides. I'm going to use that. But there are some problems with using some of these solutions without understanding all of the properties that they guarantee you, right? So in Amnesia in particular, there's two really nasty kind of edge cases. One, if your network gets, or nodes get partitioned from one another, the way Amnesia works is it will actually let you write to both sides of the partition. And when that network partition is healed, you have to choose, basically manually choose which side of that partition wins. And all the data that was written on the other gets tossed. One of the problems, of course, is that if you've returned responses to a client saying that their write was committed and you just throw it away, depending on what this is, that could be a really big deal. This condition is called split brain and is a major focus of a lot of research around consistency with leader election involved. The other side of it is this really unique edge case that sounds like it'd be extraordinarily rare, but it's actually called out in the Amnesia documentation, which means that somebody hit this. The idea is that if a power failure in a two-node cluster takes down both the nodes, one of them comes up and the other one doesn't, maybe because of disk corruption or something like that, the remaining node, using the default configuration, will hang indefinitely, waiting for that other node come up so that it can like resolve transactions that were pending when the crash occurred. And the other node will never come up because it can't. It can't restore from its data. It's corrupted or it's lost entirely. So one of the approaches to this is that you can configure it to time out when this happens so it doesn't wait indefinitely. But then the edge case is that the decisions it makes about transactions that were pending when the crash occurred is that it will make its own decisions, and those decisions may be incorrect, meaning it may abort transactions that were committed or commit transactions that should have been aborted. And if you ever manage to recover the data on the other node, there's going to be a problem when it comes up and sees that, this basically the two diverged. If this ever happens with a transaction that changes the schema of an Amnesia table, it basically renders the Amnesia database entirely unusable. Like that specific database, not like all of Amnesia. So it's a real nasty problem, and if you're not paying very close attention, these kinds of things can really bite you. So when we're transitioning to a system where we have distributed state, we have some pretty key questions we really need to be asking ourselves. The assumption is that we have multiple readers and writers acting as clients. This is not really a problem if you only have a single reader and writer, although there's still some edge cases with multiple nodes involved, but we're assuming multiple readers and writers. So how do we handle conflicts, right? That's one of the big things that you immediately realize is going to be a problem. Two clients trying to write to the same key at the same time, or somebody's reading from a key that's being written at the same time. What guarantees must clients be able to observe, right? So if I read a value and then write one, and then read the value that I just wrote, and I get something different, that's going to be really weird. But under some consistency models, that might be fine. If it's like a weekly consistent cache or something, that's not a big deal. But if you're writing like account balances or something like that, that's a big deal. The other one is do all nodes in the cluster serve requests to do writes or reads, or do all requests go through a leader? This kind of determines the path of which consistency model you're going to choose. Sorry. The second part of this is, you have to replicate the data in the first place. So how are you going to do that? How are you going to guarantee the consistency of that? What are the failure conditions that you want to be able to tolerate? How are you going to recover from those failure conditions? Do you favor availability or consistency? Do your clients always need to be able to access this data even if it's stale? Or does it always have to remain consistent? This is a super important aspect of this decision. If you're building a distributed system that is stateful, where you're sharing that state, if you don't know the consistency guarantees that you need to provide for that data, guaranteed something bad is going to happen, and it may be too late to really deal with that properly. You need to understand this stuff the minute you're trying to work with distributed state, because it really guides a lot of the decisions that you ultimately make. Here's some assumptions that you might make going from a single node system to a multi-node system: that time is accurate or reliable when it's absolutely not. It's even possible for clocks to shift backwards, particularly if you're using NTP or something, and for whatever reason the host comes up with a time that's too far ahead because its clock is really fast. It gets an NTP update, and boom, the clock shifts backwards. If you're assuming that time is monotonically increasing going forward, then this could really bite you. You might get orders or events that are ordered out of order because the clock shifted in the middle of those events occurring. As I kind of mentioned, NTP is not going to save you there. There's no global sense of time in any real sense. There's the sense of time that we perceive it. So if we're reasoning about a system, we're like, well, event A happened before event B, so logically A should be ordered before B. But to the systems that are processing those events, that may not be the case. They may not see it that way. And it's because they have their own independent views of time, and there's no way to synchronize those in any meaningful way, or meaningful way that provides guarantees that we can rely on. The other one is, I have a bunch of redundancies in my network, so partitions are never going to happen. But the reality is that partitions, particularly in Erlang, do not necessarily require that the network be the source of the issue. A major one that happens quite often if you're sending a bunch of requests between nodes is that the RPC channel, being only a single socket, can get overloaded, and heartbeats between the nodes that tell each of the nodes in the cluster that this node is up or this node is down will get hung up in that bottleneck and time out that connection. So then the nodes will think that each other are down even though they're not. They're talking just fine. When this happens, now you have a partition even though the network is fine. And it'll be like a really fast partition probably, but still, you need to understand what that's going to do to your system. The other one is that messages are always going to be received in the order that they were sent. That's not necessarily the case. Maybe with synchronous calls, you might be able to count on that, but not with broadcasts or multicasts. If you send a message and then you're waiting for some kind of response, like an acknowledgement of some kind, it's possible that you will get an event in the wrong order. These are things that your system needs to account for. You can't be assuming that you're going to get orders in the exact same events you send them, because maybe the first event that you sent, a write, goes across the fast link, or slow link, sorry. The second write you make goes across the fast link and actually arrives before the first message. And if those writes were related in some way, that might violate an invariant of your application. And of course, assuming that your file system is reliable and won't corrupt data, that's not going to help you. And you can get really weird things, like the host just flip-flops, powers on, powers off really fast for some reason. Maybe the rack is getting flaky, or somebody tripped over a cable, who knows. So here's a few examples of the kinds of things I'm talking about. Like if a client makes a call to a server, and the server starts processing that request, but before it can send a response back to the client, that connection gets dropped. The client may think like, oh, that request failed, I need to retry it. But the server's still processing that request. So the client makes that request again, and they end up processing the same event twice. Depending on what that event is, that could be a problem. So that requires some special handling, right? That requests are idempotent. You can't replay the same event multiple times if it's something that potentially has side effects. The other one is that if a server blocks expecting some kind of event from another node, and that message that it's expecting gets dropped on the way, that server will just end up deadlocked, waiting forever. Another one, which I think bites people more often than not, is the idea of dynamic node membership with leader elections. One of the key principles of leader elections is that you need a majority of nodes to agree that you're the leader, and also to agree just in general on decisions. And so when this happens, if you allow nodes to just arbitrarily leave and join the cluster, and a partition event happens, then from both sides of that partition, nodes will readjust their internal view of the cluster, and now they will consider that they have a quorum of nodes to elect a new leader. Now you have two leaders, both on sides of partitions, accepting rights and committing them. When that partition heals, you now have a conflict in that data that was written, and data is going to get lost. It may not be possible to actually heal the cluster properly without some like surgery, basically. This is a major focus of protocols like Raft and Paxos to ensure that these guarantees are never violated. So you might be tempted to throw leader election at a problem to like make it easy to just say, okay, well, this node will always make decisions about rights, and we don't have to really think about potentially multiple nodes trying to write to the same value at the same time. All the requests will be serialized through a single process. Well, you can't guarantee that that's going to be true in a partition. So you just can't kind of pick and choose the aspects of a protocol that you want. So when we're doing this, like, we're either building a protocol ourselves because we're in some sort of unique situation, or we're using one that's on the shelf, a library that's already available, or maybe we're implementing a protocol in a library because it hasn't been written yet. But the big question is, like, how do we test and verify both the protocol implementation, if that's our responsibility, or if we want to verify a library before we try and use it in production? And then on top of that, how do we verify that the stuff we're building on top of that protocol doesn't violate some assumptions that it makes? We need special tooling support really for this. And we don't have it. You can kind of build your own stuff, but there's nothing in there that makes this easy or convenient. I think is sort of a major oversight, really, in a language that, kind of on the label says that it's built for distribution. It is super easy to believe that you've implemented a protocol correctly when you've made some assumptions that actually aren't true about the environment you're running it in. For example, a lot of protocols and like the papers that you'll read will say some assumptions like, we're assuming that in this model, messages are never reordered, but they can be dropped. Well, if on your network messages can be reordered, now the guarantees of that protocol are completely moot. You can't take and use it in your environment because it's just not true. It's not useful for you. So you have to be really aware of those things. Aware of the environment that you're planning to run your software in, aware of the guarantees provided by a protocol and the model under which it's built. And one of the things that we really need in this area, because of these problems, is a way to effectively verify that those guarantees that we thought were true actually are true. So real quickly, I want to talk about consistency, just to catch people up that aren't necessarily fully aware of all the different flavors of this. Consistency basically defines the order in which reads and writes are observed to have occurred. And sort of like the logical definition of this is that given an execution, which is basically a set of nodes and some sequential set of operations, reads and writes, that occur at each node, something is considered consistent by some model if a test of the guarantees of that model passes against that execution. That's a real mouthful, but hopefully that kind of intuitively makes some sense, right? If a model says like such and such will happen when I send a write to this server, then given an execution with those writes and reads, we should be able to observe that that happened. And if that doesn't happen, then we know that we violated the consistency guarantee for some reason. We don't necessarily know why. So here's kind of this isn't like the full set of all the different variations, but these are the main ones kind of from my perspective. Weak consistency basically says that there's no real guarantee about ordering. Events can be processed on any node in any order, and however it shakes out is how it works. So it's not particularly useful, but it's useful in the sense of being able to describe how your system functions. Eventual consistency is like kind of a step above that in the sense that it also doesn't necessarily guarantee ordering, but it states that eventually the cluster of nodes will converge on some order for concurrent writes. The definition of a concurrent write is they're not related, versus writes that are related using something called a happens before relation. If you have an event A and an event B that occur on the same node, and A happens before B, then A happened before B, using that relation. So when we say that something happens before, that's what I'm talking about. When we say it's concurrent, it means that they don't affect each other in any way. So it doesn't matter what order those things are processed in necessarily. So eventual consistency basically says that for concurrent writes and reads, it doesn't matter in what order that they shake out. Causal consistency is a further restriction on that, a stronger guarantee that the order that it converges on reflects that happens before relation that I was talking about. Causal plus is yet again a stronger constraint on that says all of the nodes in the system will agree on a single order for all events. So it's fairly strong, actually. But it doesn't say when that will happen. It could, like all the nodes in the system may take a long time to reach that agreement. So it's not an immediate thing. It means that clients in the system may observe things that are stale. But if all you care about is the end state of the system, then that might be good enough. And then we get into the ones that are more familiar from like your standard relational database terminology, the idea of serializability, linearizability, strict serializability, and sequential consistency. Serializability basically just says that the events can happen, concurrent operations can happen in any order, they can be reordered, but there will only ever be a single order observed by all nodes, similar to causal plus in a way. Linearizability says that writes will appear to happen like immediately. There's never a time where a write has happened and nodes don't observe that write. And linearizable reads, it's a similar thing. Once you've read a value, you can never read an older write for that value, only newer writes. So it's the strongest guarantee, basically. Strict serializability is the combination of those two things. Basically says that the total order of all events in the system will reflect the real-time order in which they happened, as perceived by us, not necessarily the system. Sequential consistency is basically a slight weakening of linearizability that says that it doesn't have to reflect the real-time ordering of events, but that there will only ever be a single order observed by all nodes. So a ton of stuff, sorry. And then there's a handful of client-oriented ones. These are things that are guaranteed from the perspective of a client. The idea of monotonic reads and writes means that, like, again, with the reads, like if I read a value, I will never again read an older write than that value reflected when I read it. Only newer writes. With monotonic writes, it's a similar thing. Once a value is written, it's never possible to read an older write. In other words, you can't like change history for a read. And read your writes kind of is what it sounds like. If you, as a client, make a write and then read that same key or that value, you'll get the value that you wrote, or a newer write. And writes follow reads just means that if you write a value, then read the value, then write it again, it's not possible for the second write to change the history of the read that you performed. And availability is sort of like another critical aspect of this. So you can't have a highly available system and a strongly consistent system in the sense that, like, linearizability. They're mutually exclusive in that regard. You have to choose somewhere on a spectrum between the two. And it's a balance between how strong of a consistency you need versus how highly available your system needs to be. And all this is just a definition of the ability of a system to actually basically respond to a client that says, like, yes, your operation was performed, or no, it wasn't. And it's defined in terms of the conditions, failure conditions under which it holds. And you got this idea of always available, which is typically what we mean when we say highly available. Sticky available, which means that if you're always talking to the same server as a client, operations will always complete. And quorum available, which is kind of what happens under a leadership situation where you need a quorum of nodes to talk to, and all the members of that quorum need to be able to reach each other. And here's one I don't think people hear about too much. It's the idea of convergence. This is sort of separating the idea of consistency from the idea that data will eventually reach some value. And the definition of this is really the ability to ensure that writes made on one node are observed by all nodes in the system. So it's also defined in terms of the conditions under which it holds, failure conditions, and is usually, what people are talking about when they mean eventually consistent. People are talking about the idea that those values eventually converge on some single value. And again, this is sort of the definition of the balance between consistency and availability. What is the ability of our system to converge on values? If it can't, then it's weakly consistent. So it is absolutely essential that you understand the three properties that we just talked about, just looked at, and the guarantees which your system, in terms of these things, have to uphold. And that seems like a lot to have to deal with. Like you wanted to go from a single node to multi-node, and now you just open up this whole like Pandora's box. And I think that it can be a lot easier than it is today. It does not have to be a research problem. I mean, unless you're actually doing research. It should be something within the reach of anybody that's building an application. Like distributed state shouldn't be this puzzle that everybody has to figure out from scratch each time they're building a new distributed system. And for that, we need proven foundational tooling that we can build all of our distributed state abstractions on top of, or at least use to inspect them to make sure that they're actually doing what they're supposed to do. So one of the things I've discovered this year, and I kind of had a feel for this before, but I really had to confront it, is the fact that it is super difficult to just run automated tests against a cluster of nodes for any non-trivial application. There's basically no tooling whatsoever for it. There is in Common Test, the Erlang test library, but it's fairly simple stuff. Like I was able to port it to Elixir quite easily, but then you have the problem of like, well, how do I accurately simulate faults in some sort of randomized fashion? And all the like foundational stuff is there to build these things. It's just nobody's put them together, as far as I can tell. But even the idea of randomizing faults to see what happens is not good enough to guarantee that your system actually will behave the way it's supposed to under all combinations of those faults. Just that whatever set of those you actually performed are safe. And the state space to explore via randomized testing is just ridiculously huge. For any non-trivial system, it's basically an impossible problem. I mean, eventually, if you run your test long enough, you'll probably uncover all the problems. But how long are you going to have to run those tests for? The other aspect of this is that it shouldn't be the case that we're constantly building new abstractions from scratch and throwing away everything that other people have already done to try and model test things or build some abstractions to share these pieces that have been verified. And we need a way to verify that stuff, like tooling to actually perform the verification. There's model checkers, there are property-based tests, concolic testing even, but I don't think that that's necessarily the right fit for this. So the project I've been working on for the last month is called Cadre. I don't know why I named it that, it works. Basically, Cadre is like a group of highly specialized, individuals for some specific task or job. And I kind of think of, processes participating in a distributed cluster is basically that. Highly specialized for replicating data across the cluster. So that's kind of the idea here. I built it on top of a discrete event simulation framework, which was also part of the library. The idea was to sort of model this after the way Foundation DB was written, which is a key value store built by, well, the Foundation DB guys, but then they're bought by Apple, and now it's like open source. But they did the same thing. They built the simulation framework from the ground up. It was in C++. We used like a custom, basically, preprocessor language to build actors that are then compiled into a synchronous form for testing. So I took that idea, like we have processes in a system and we want to be able to model them in a synchronous way. Rule out any non-determinism in the system like time, randomness, message sends, all that stuff needs to be handled by the simulator so that we can step through it, and not just step through it, but be able to rerun a failure case with the exact same inputs and produce the exact same failure. That allows us to basically step through the problem, inspect it, perform a fix, and then rerun the exact same test to make sure that it either was fixed or failed because we didn't fix it properly. And part of the abstraction Cadre provides is pluggable persistence, so you can have different storage layers like in memory, on disk, whatever. But this is implemented as a key value store with ordered set semantics, meaning that the keys should be sorted in lexicographical order on disk or wherever it may be stored. The key there is that it allows you to build higher level abstractions on top, like indexes, using that sorting. It allows you to do things like range reads based on time or names or whatever. And then pluggable consistency models, so I can have a distributed map that's backed by Raft for strongly consistent implementation, or one that's backed by an eventually consistent model because I need higher throughput, but don't necessarily care if consistency isn't totally strong. And the idea of a store, which is really the application level state machine or rules that the store is built on. In the case of like a distributed map, it would basically be like map.put, map.get, map.delete. It's really straightforward from that perspective, but it can be arbitrarily complex depending on what you're trying to do. For example, one of the things I'm planning to build on this, is taking Swarm, the global process registry that I built, and basically rebuilding it on top of this. And a process registry has a fair amount of complexity to it. You need to be able to monitor processes and determine whether or not that process exists, and you need to be able to maybe send to a group of processes under some group name. If you're curious about that, you can look at Swarm or Horde or Sen. All three of those are eventually consistent global process registries. And the last piece of this that I'm most excited about, and really why I'm here, is the idea of lineage-driven fault injection. This is a topic of a research paper by Peter Alvaro and I think some of his students, or I'm not sure, I don't really want to offend them, but a couple other guys. And the idea is that given some execution of events that have occurred, you should be able to determine the provenance or the source of where a correct outcome came from. So if I say, perform two writes, V1 and V2 is the values, and the correct outcome is that all the nodes in the system see V2, then I should be able to see, okay, that happened because on node A, it saw V1 and then saw V2, and then it sent those to nodes B and C, and now all three nodes agree that V2 is the value for that key. And by working backwards from the outcome to the source of that outcome, or at least the supports for it, lineage-driven fault injection can target the things that supported that correct outcome. So if, for example, it sees that, okay, it required a message send from A to B and from A to C in order to replicate that value, what happens if I drop the messages between A and B and A and C when it's trying to perform that replication? So kind of these are the general goals. I think I'm going to skip over this because I don't have a lot of time. The way to think about lineage-driven fault injection, though, is really this idea of a game between you and a malicious system, like HAL 9000. Somebody who's like, I'm going to break whatever system you throw at me. So you're playing a game with this malicious system where you have to feed it a program, and it tries to break it, and you win if it can't break it, and it wins if it does. But in the process of it winning, it has to provide proof to you, a counterexample that shows the failures under which your correct assumption fails. And the idea behind this model is that fault-tolerant systems are redundant, right? So as a naive example, one way of achieving fault tolerance for something, when you're making requests from some client to a server and that request fails, you might retry it with an exponential backoff to attempt to try and establish that, get a successful result from that request. So the idea of this redundancy being sort of the source of fault tolerance is the thing that LDFI targets. It finds the redundancies that supported the correct outcome, injects faults to basically delete those redundancies, and then sees what happens. And there's a lot of like math basically behind it, but it can prove that if it can't find any faults that it can inject that produce an incorrect output, that to the execution depth that it tested, your model is correct. Like it has no known problems, no possible problems. Now, it's always possible that given some arbitrarily deep execution, you might eventually encounter a problem. And so the idea is that if you really want like a fairly solid proof, you let this thing run for quite a while. It's not quite as exhaustive as a model checker, but it comes real close. And it's, I think, a lot more achievable for something like this, and would at least get us closer to a world in which we have both something like this for targeting in on failures and actually a model checker. So the way you tell LDFI what it needs to check is you give it a pre and a post condition. Like given something, the precondition being true, the post condition must also be true. And it will figure out what it needs to try and do to falsify the post condition. If the precondition isn't true, then it's like called vacuously correct. It basically means it doesn't matter. It's an irrelevant assertion. So it only cares about if the precondition is true and the post condition is false. So as a quick example, like in Raft, the way the leader election works is a candidate for a leader sends out a request vote RPC, and all the followers have to grant a vote or reject a vote. There's some criteria around that, but one of those criteria is that if a follower is granted its vote to some candidate, it can never, within the same term, grant another vote to another candidate. And this principle prevents multiple leaders from being elected. And so kind of the blue versus the red here is the precondition versus the postcondition, if that helps to visualize it a little bit. One of the things that LDFI can produce is diagrams like these, which show an execution, the set of nodes, and like this is time going from the start as you go down further forward in time, and events that have occurred. So this is actually an example of a fault that LDFI caught via an implementation of it called Molly. I found this fault in Kafka, actually. Basically, the idea is that nodes that are participating in a cluster, like that cluster definition is stored in Zookeeper. And if those nodes get partitioned from Zookeeper, it will assume like, oh, they're not part of the cluster anymore. And so it removes them from the group, that configuration. And then the remaining node thinks like, oh, well, I'm the only node left. So I'll just continue to be the leader and serve writes and reads. And so it accepts some writes. The problem is that when the leader fails, those writes are permanently lost. And so, as they point out here at the bottom, it violates the principle of durability that Kafka is supposed to provide. So these are kind of the last remaining things I am working on before I release this. It's not open source yet because I'm still working out some API things. I'm trying to figure out the best way to surface some of these pieces in a way that like is consumable by pretty much everybody. One of those things is the provenance of events that happen in the system, being able to actually trace everything that happens. It's already the case that the simulator stores an execution log of every event that occurs in the system, but there's no idea of inheritance, like lineage between the events, and that part I still need to add. And I need to add support for message delay and reordering because that's a particularly interesting case that can trigger quite a few failures. The model I've been working with is actually Chris Keithley's Raft implementation. I've been using that to just test the simulator and run some scenarios. As I want to help him finish up his implementation because it's missing some of the extensions that are provided in the more recent versions of the paper, namely cluster management, RPCs, and snapshot RPCs. But I want Raft to basically be an out-of-the-box option with this. So if you pull in this library, you'll have two options, an eventually consistent or causally consistent one, and raft for a strongly consistent one. And over time, I'm hoping that more consistency models would be developed by other people. So helping finish up the raft implementation so it's complete, and then I've started a causal plus consistency model as well that I need to finish up. And the idea of LDFI parameterization is you need to feed the LDFI algorithm the pieces it needs to know, like when it should stop, like consider that it's exhausted all possible opportunity to find faults. And by automating this, it makes it really easy to consume. You basically turn it on, let it run against your implementation, and it will either produce that counterexample graph diagram like I was talking about, or it will say, hey, everything looks good to me. So yeah, wow, I managed to cram it in there. Amazing. I don't think I have any time for questions, unfortunately, otherwise, but I mean, come find me if you're curious about things at all. I know that that was a lot of information to try and soak up at like 4:30 in the afternoon, but.
Yeah, I think we might have time for like 1 or 2 questions, because I'm not going to say much. Oh.
It's kind of a simple question, but I don't think I caught sort of an idea of like how long an individual check might take, like how long it might take to sort of test an implementation. Is this the sort of thing that you could put in your CI? Or,
absolutely, yeah. It is extremely fast because it's not running randomized faults. It's finding things that it knows will cause a fault if there aren't other hidden redundancies. So like one of the things that might happen is that you send an event from A to B, and if LDFI drops that message, but your implementation is like, oh, that message got dropped, I'm going to resend it. LDFI is be like, oh, well, I thought that counterexample would work, but it didn't work. So now I'm going to produce another one based on this new knowledge I have. And so it iterates back and forth until either it exhausts all possibilities or hits like a maximum timeout. But it's very fast because it doesn't have to randomize anything. It's just like picking things that either must be a problem or can be falsified.
Cool, thank you.
Yeah.
Over here. So you're working on a pretty fundamental problem, or on a solution for a pretty fundamental problem. If you'd have to speculate, what would be your guess why this attempt hasn't been made before, or failed before?
Why it might not have been made before?
Yes.
Well, the LDFI stuff is really new. I think the paper came out like only a couple of years ago, and it's still a topic of ongoing research, basically. And the other area of research is the idea of data provenance. Like the lineage-driven part of this is based on database research and data provenance. And that was kind of what inspired Peter Alvaro. So I think a lot of it's just that this idea is fairly new. In Erlang even, we have quick check modeling, property-based tests, and then there's that concolic testing library, Conquer, that's out there. I haven't tried using it in Elixir yet, but it's available for Erlang. So there are some attempts at trying to solve these problems, but I don't think anybody has tried to target this specific problem, the idea of protocol verification instead of I'm trying to verify the whole system. This is not an attempt at making sure that everything that's running in the beam when your application is running is correct. It's verifying that the model that you've built is correct. And I think by focusing on a more specific problem, we can solve a large class of errors without necessarily trying to, tackle everything in one solution.
Okay, if anybody else have any questions for Paul, Well, yeah, that's what I'm saying. We have a happy hour at the Batch Bar at 5 to 7. It's hosted by Rovery Labs. The Batch Bar is in the Hyatt Centric, which is our partner hotel. So we'll be heading that way. So those drink tickets, yeah, make sure to use, hold on to those and use those there. But everybody, thanks, Paul.
Thank you.